So the presentation you're going to get today is based on one that I give to students. And so I talk a little bit about myself, and I try and get them to take a risk, put themselves out there. And sometimes that's difficult. Many of them are afraid of making mistakes. We train kids at school that getting the right answer is the most important thing. That's not necessarily the case. You really want them to be able to use their imagination and their creativity in order to try and find solutions to problems. Einstein understood this very, very well. Imagination is more important than knowledge. You'll see that occasionally I pull in ideas from people who had really brilliant ideas along the way. A little bit about me. I was not a native English speaker. When I came to the United States, the only language I spoke was Japanese. And the first day that I had to speak English was actually my first day that I went to school. I was born in a really small fishing village. This is a photo of the town. And that little tiny greenhouse at the end of the way, that's where I was born. My mother grew up there as well, my grandfather. And so it was, my father was an American serviceman, and there was a navigation aid station there that he was in charge of some of the maintenance for. And that was how my father and my mother met. And it took us about 4 years to figure out how to get into the United States at that point. I really loved airplanes from a very young age. My parents talked about this a lot, and I was pretty good at math and science. We ended up here in Southern California when I was very young, and the 9 years that I grew up here, that's when I think of as having grown up here in Southern California. There was a new sport on the sand dunes here at the beaches in Southern California, was hang gliding when I was young. And at the age of 12 years old, I built my first hang glider. That's a photograph of me on my second hang glider flight, actually. And we moved overseas shortly after that while I was in high school. And it turns out I couldn't fly hang gliders anymore, but they did allow me to fly sailplanes. And that was where I made the leap into sailplanes. And we were overseas in Australia at that time. My career at NASA, I came back to the United States, got my degree in aeronautical engineering, and then I was a graduate student, and NASA helped me with that. And I studied inverse airfoil design methods. I was hired full-time in 1983. That's a list of some of the aircraft that I ended up working on. The oblique wing, the deep stall, F-111 mission adaptive wing, the controlled impact demonstrator. That's the airliner that's crashing there. I was responsible for some of the approach aerodynamics during that particular test. We were testing a fuel that wasn't supposed to burn on impact. And as you can see, that was a failure. One thing that we did learn was that the seats that the airliner passengers sat in, we had about 102, as I recall, test dummies in the seats, fully instrumented. And we discovered that the seats would survive the crash, but that the people that would be strapped into them would end up breaking their legs or their hips or their back because of the strength of the seat. And because of that, there has been a push to try and change the seats so that the seats now absorb the energy by failing in a graceful manner and allowing the people to survive rather than the seat. And so if the crash is survivable, as this one would have been, people can then escape from the aircraft. That was one of the things we found. I made the mistake of moving into management in 2002, and I moved up we call it the food chain, up to the chief scientist role in 2014. I worked on the SR-71. I worked on the thrust vectoring for the F-18. We did an aero tow experiment on an F-106. We worked with JPL on an aerogravity assist maneuver, and we had a simulation that we built up. And then at the end, I started working more on this, how do birds fly without vertical tails? And along the way, we had, because we are the flight research organization, when astronauts would retire, many of them were test pilots, they would come back to our place. And so I had the opportunity to interact with a number of astronauts over the years, including a handful of Apollo astronauts. I got this crazy idea that I might be able to collect the signatures of all 12 of the astronauts that had walked on the moon. And I did that fairly easily. It was somewhat surprising. And 4 of these signatures I was able to get personally. They signed their signature for me. And so I ended up collecting all 12 of the astronaut signatures that walked on the moon. This is me with Buzz Aldrin. That's Jim Lovell signing my his book for me. And then down there at the lower right is Vance Brand. Vance Brand was an Apollo rookie. He flew on the Apollo Soyuz mission. He was a backup or a support crew member for 5 different Apollo missions prior to that. And Vance is a very good friend. We still talk. He still lives here local in Southern California. And I haven't seen him in the last year at all because of COVID, but I'm looking forward to the ability to get together with Vance sometime soon. I was interested to hear that you're doing this mostly for young women, so this is appropriate. I'm not the only one that was a space crazy kid. This young lady that is sitting in front of Scott Carpenter. Scott Carpenter was the 4th American to fly in space. This young lady, her first name is Rebecca. She was one of my interns. And I'll show you photographs of her later on. And she's married now. She's pregnant with her first child. And but she was one of my brilliant interns that I had along the way. I had 170 of them work on this problem. And really awesome having this very diverse group of young people come in and work on this problem. And in my reports that I've written about how birds fly, I've included the names of all of my interns. And so it's something I'm actually very proud of, that these kids have done so well. Let's talk about minimum drag just for a minute. This is Peter Drucker quote. The important and difficult job is never to find the right answer. It is to find the right question. And he's trying to make a point that much of what we do is actually misperceived. We think something is important when in fact it is not. And so we expend a lot of effort on trying to find the answer for things that really are not important to the question that you're trying to solve. And of course, we're trying to solve this problem with birds. So I'm going to start in an unusual place. This is called the Breguet range equation. The range of any air vehicle is simply the efficiency of the propulsion system, and then the efficiency of the aerodynamics, and then you have a weight fraction. And you'll notice that landing weight all the way over there on the right side. And what this says is you actually want the most aerodynamic efficiency for a given structural weight. Your landing weight is mostly the structure. And so you have this efficiency, aero efficiency versus the landing weight. And this right here encapsulates the exact problem that you want to try and solve. Because I'm going to tell you here shortly where we misperceive what is important. And that was what led me to discover the right answer for what birds do. And there's a wandering albatross. This animal has a wingspan of almost 4 meters. They're just short of 4 meters in wingspan, 3.8 meters or so. They weigh about 20 pounds. This particular bird right here is pulling about 3 Gs at the bottom of a dynamic soaring maneuver. And you can see that even though it's pulling 3 Gs and the water is not smooth, you can see how the bird is able to just exactly touch its wingtip to the edge of the water during this 3G maneuver. And they do this about 3 times a minute. Every 20 seconds or so, they repeat this maneuver over and over while they're doing their dynamic soaring maneuver and extracting energy from the boundary layer that moves over the ocean. We don't know how long these birds live. We think it's more than 80 years. We don't know. It's amazing what we don't know about these animals. They're truly magnificent. It wasn't until 2012 that we discovered how it was that they did the dynamic soaring maneuver. So that's only 9 years ago, and Gottfried Sachs from Technical University of Munich was the one that published that paper. And definitely worth digging up and reading. Um, he he uh, he is a aircraft dynamics professor, and it just so happens that he was studying the flight of birds as well. So along the way, why do we put vertical tails on and birds don't have vertical tails? So you can see here Wilbur and Orville Wright. These are their 3 flying experiments down the left side. You notice there's no vertical tail. The last one down there at the bottom is the 1901 glider. And Wilbur and Orville flew that glider hundreds of times and crashed it hundreds of times, because every time they would try and turn the aircraft, they would create more lift on one wing. But as they created more lift, it would create more drag, and the nose of the aircraft would yaw the wrong direction instead of lifting that wing and turning in the correct direction. And they crashed hundreds of times. And on the train ride back to Dayton, Ohio, this happened in Kitty Hawk, Wilbur tells Orville that man would not figure out how to fly for 50 years. So they come back the following year, but they've now added the vertical tail. And Wilbur believes that if he actuates the vertical tail, that he can control the yaw of the airplane to keep the nose of the airplane going the direction that it should go. And they began flying this glider on October 10, 1902. And the last flights that they make, and this is a photograph from that day, is the 26th of October, 1902. So all the flights that they made that year were in 16 days. And they ended up flying about 400 times in that particular October in 1902. They took 2 photographs on this last day, and the Wrights took their photographs for a very specific reason, so that the notes that they had plus the photographs would prove that they actually did what they claimed. You'll notice that the wingtip looks fat on the left side, and on the right side, the wingtips look thin. And the reason for that is the Wrights used wing warping in order to be able to affect their roll control. This photo, you'll notice the fat wing is being lifted up and the thin wing is actually being dropped down. And if you expand the photo dramatically, you can actually see that the rudder is also turned. These are the first photographs of a human carrying air vehicle in a coordinated turning flight. And it was the Wrights that did this. They stopped flying this day, and then they came back in 1903, and of course, everyone knows the photograph of the 1903 Wright Flyer. In 1906, the Wrights patented their airplane, and that's the diagram at the lower right out of the patent. You'll notice there's no engine, there's no propellers. That's not the piece of the airplane that they were interested in. It was the control of the aircraft, to be able to control the roll and the way that they used the rudder. There was a misperception at that time because everyone thought that airplanes would turn the same way that trains did, and automobiles for that matter. A 2-track vehicle simply turns its wheels and it moves in yaw. That's not the way aircraft turn. Aircraft bank to turn, and the Wrights understood this because before this, they were building bicycles, and they understood what it was to bank in order to be able to turn, and they were trying to do the same thing with the airplane. Okay, why did they have this problem with more lift and more drag? So Ludwig Prandtl is the first one that comes up with an analytical tool, and he calls it the lifting line theory, an analytical tool for wings. Prior to this, if you changed the wing, you had to go back into the wind tunnel in order to see what those changes did. Prandtl gave us the tool that allowed us to calculate what the effect of changes to the wing would be. Once you have a tool that you can do this with, of course, engineers, we love to do optimization. And so Prandtl quickly figured out that the elliptical span load was the minimum drag for a given wingspan. And one of the outcomes of that is the downwash in the wake of the wing is constant from one wingtip to another. So, and this, by the way, becomes the standard theory for the minimum drag of wings. because it's the minimum drag for a wing of that wingspan. But as we just saw in the Breguet range equation, we know that that's not necessarily the answer we're looking for. And it results in something different. We all know that the feathers on birds are very soft at the tip. And so we know that you can't carry a very large load. This particular case, the elliptical load, there's a very large load that disappears very abruptly right at the wingtip. And because of this, we have wingtip vortices. And we still see this. Aerodynamicists love these photographs. One of the worst things you can ever do is go to a dinner party and ask an aerodynamicist, what about those wingtip vortices? It will be the last thing you talk about for 2 hours. And there are hundreds, if not thousands, of these photographs on the web because of this particular way that we design aircraft. Sometimes you can see the elliptical load itself. And on rare occasions, you can even see both. And of course, aerodynamicists love this. But along the way, we've forgotten something fundamental about the way birds fly. And we no longer look to birds as a model for flight. Why is that? What is it about these birds that allow, look at the feathers there. The feathers are straight. So there isn't a large load that's disappearing right there at the wingtip. There has to be something else. In fact, you might even think that the load would come down and taper to the tip. So it turns out that Prandtl did another solution for the minimum drag problem. And he did it in 1933. And you'll notice that curve C on there is his new solution. You'll notice out there at the wingtip, the load comes down and the slope of the load goes to 0 just at the instant that the load itself goes to 0. And this is a different way of thinking about the load. And if you think about the feathers on a bird, you think perhaps this load could be the way that it works. There's also something else that happens. The load is convex downwards to a certain point, and it turns out it's about 70% of the wingspan. And then the load becomes concave upwards. And so you have this inflection point that's at about 70%. There's a reason for that. Down at the bottom is the downwash, and Prandtl writes this as the wash, W, it's down. And so the curve A you can see is the elliptical, and you can see the constant downwash all the way out to the wingtip. The curve C, you'll notice, bends up and becomes upwash at the wingtip. This curve C, by the way, is generated from the same structural weight as curve A. The weight between those two wings is the same. The way Prandtl did this was he used the integrated bending moment as an analog for the structure, as a model for the structure. And by doing this, he ends up with making the weight of the wing being the same. This curve C, by the way, is a 22% increase in span with an 11% decrease in the induced drag for the same structural weight. I often get aerodynamicists who insist that that's not the minimum drag for that wing, that you could put an elliptical load on there, and I have to point out that you can no longer do that with the same structure. You change the structure by doing that. Here we've kept the structural weight the same for the two solutions. And so this becomes the minimum drag solution for a given structural weight. Any other solution that you would come up with for that amount of structure would have a higher drag. And we've actually done this. I've done this experiment with my students. They go through the analysis and they change things just ever so slightly, and you can actually see that this is actually the bottom of, we call it the drag bucket. You're at the very lowest point of this particular contour. So this is the actual derivation that Prandtl does. The amazing thing is Prandtl never references this paper again for the rest of his life, 20 years actually. And there are only a handful of references made to this particular paper. And some of the people we're about to talk about who studied things around this problem also didn't do anything with this particular solution other than to mention the fact that it existed. So here's Horten. Horten built a series of sailplanes in Germany and then later in Argentina after World War II. Horten used a span load that was similar, but he constrained the wingspan to be the same. And so he accepts an increased drag over the elliptical span load by doing this. You'll notice there in the induced drag, though, all the way down there at the tips, there's this little tiny part of the induced drag that becomes negative drag out there at the wingtips. And when I would read this paper, by the way, my head would hurt before I understood the problem. And I could not see how that you could end up with negative drag. And I had this stack of 6 papers that were sitting on a folder on my desk. And I would just read these papers and I would struggle with them. And I knew there were pieces that were connected between each of these papers to the problem, but I could not figure out what the connection was. And I always thought that these people understood this, that they were, to them, the problem was trivial. And in fact, that's not the case. I remember when I finally did figure this out, that it was actually quite terrifying for me, that I realized as soon as I had figured this out, that I knew something that none of these people did. And that was a very scary thing for me. R.T. Jones, great American aerodynamicist, worked for the NACA and later for NASA. I got to meet R.T. Jones when I was working on the oblique wing. That was also his idea. Here, he constrains the wing root bending moment. So it's only one point on the structure. So it's a unique solution that is related to the one that Prandtl did. Jones published this result in 1950. Klein and Viswanathan published a minimum drag paper where instead of using the bending moment, they used the integrated shear on the wing in order to try and constrain the solution. Something I should mention unique about this particular result, all of these people that I'm talking about here are dead, except for Satya Viswanathan. He is still alive. He's 73 now. He's actually very funny to talk to, hilarious. And we should probably call him up and find out how he's doing. He runs a desalinization plant in India, where he's from, and he provides drinking water, fresh drinking water to the city where he lives in India because of this desalinization plant that he's created. And this was one of the last solutions that got solved. When he heard that we were actually building some of these vehicles in order to try and look at the span load other than the elliptical, he got very excited. It was actually quite funny. It was an amazing thing talking with him. The one other paper beyond this that I had was the paper by Richard Whitcomb, the other great American NASA aerodynamicist, who invented the winglet. And this particular page that's on the right is out of one of my textbooks, and it's referenced back to Whitcomb. And I have all of Whitcomb's papers that are on winglets and a couple that were not published, actually, from his proteges that I knew. And this diagram down at the lower right does not exist anywhere in any of Whitcomb's papers, but this is exactly what's going on, that there's actually a negative drag component that is being created from the winglet, sticking up vertically into the wind. And it's because of the vortex at the wingtip that's causing this upwash flow field that allows this negative drag component to exist. I believe that this particular textbook was written by Barnes McCormick out of, he's Canadian, that he had actually drawn this diagram in order to explain what was going on. And even though Whitcomb had all this data that pointed to this solution, Whitcomb never said this. And this was the key piece that I suddenly realized how you could get an induced upwash on a particular part of the wing, and that you would end up with a negative drag, that you would end up with thrust. And this is what birds were doing, because if you increase the lift in this case, you would increase the thrust. And if you could do this, then as you would lift the wing up, that wingtip would move forward and you wouldn't have need of a vertical tail. And these are all the pieces, by the way, in the early 2000s, I figured all this out. And this was the point at which I realized I knew something that none of these other authors, they hadn't connected all the dots from one to each other. And I have photographs of Prandtl and Horten talking. And seeing photographs like that, it will throw you off, because I was convinced that they were working on the same problem and they both fully understood what they were doing. And in fact, they were talking past each other and there was no connection between the two, and even though those two solutions look very much the same. All right, so moving on. Uh-oh. Wow. Let me see if I can't do something here. Ah, okay. How would we prove this? Okay, we need flight mechanics to show this. We call it proverse yaw instead of adverse yaw. How would you quantify the amount of proverse yaw, and where in the envelope would that occur? And then could you prove that you were actually getting the aerodynamics that correlate with Prandtl's 1933 paper? And then we wanted to show the connection between Prandtl 1933 and bird flight. And so what we ended up doing, when I first calculated this, I couldn't believe it would work. I knew what rudder pedals were for. I flew sailplanes, and having that understanding, I knew that if you just used roll control, that the yaw would not be correct. And I had a student working for me at that time, a kid named Mike Allen. In fact, I had a short conversation with Mike this morning on Facebook. And Mike said, give me those numbers. I know this will work. And so he went home, and over a very long weekend, he built this little glider, radio control glider, and we went out and flew it. And the photo over on the right, you can see Mike standing there flying the little glider, and you can see how bird-like the wing looks as it's flying. And this little glider, I abused this little glider badly while it was flying to try and show that it would misbehave, and I could not get it to do that. This thing flew exactly the way birds flew. So this is what it would look like. Here's the upwash at the tips and downwash in the middle. So if you ask yourself the question, well, if this is what it is, then where would the vortex be? Because it's not going to be at the tip. There's no load at the tip. So there's no difference in the pressure between the upper and lower surface that would cause the flow to create a vortex. And if you stop and think about it, perhaps it's where the downwash crosses over to become upwash. So we freed up the wake, and Marko Stomenovic, by the way, is a friend of mine in the Czech Republic. And he's the one that actually did these diagrams when we were talking about this. And you can clearly see that that's where the vortex would be. So we went out and we put tapes on our little glider, and you can see the vortex at the 70% point. We've launched these gliders with a very large rubber band. You can see it's being towed up right here by the rubber band. And you can clearly see that the vortex is right there at about the 70% point. If this is what birds would do, then birds should fly with their wingtips overlap. And we figured this out first by looking at the aircraft and the vortex photos. And then we started finding all the papers that were on birds and talking about the overlap of the wingtips. These are California brown pelicans. And these are, they're about 32% of wing overlap is the average for this entire formation. It turns out others had published their data on this. Jeff Spedding, a brilliant guy from Bristol in the UK, and he found that the Kestrel had its vortex cores were about 0.76 of a wingspan apart. And if you assume elliptical, then the only way that vortex could come from the wingtips is if it would immediately pull into that 0.76 of a wingspan apart. It turns out Jeff Spedding is a professor down at University of Southern California. I did not know that until 2015. And so I actually went down to USC and I met Jeff Spedding, and we talked about this. And he invited me to come down and speak to all the professors about what I had found. And I made that presentation in October of 2015. And since that time, USC, I believe, is the only school in the United States that actually teaches this. There was a paper in 2014, January 2014, published by Stephen Portugal and Jim Usherwood, and they were looking at the northern ibis. And again, they were looking at all the way down here in the lower right, what the overlap was between the wings. There were other people that had done similar things, Hainsworth, Cutts and Speakman and Banks. And if you take everybody's data and non-dimensionalize them in the same way for wingspan and for frequency, then you get this result where I've taken all the data and just overlaid them. The green line on there is Prandtl's 1933 upwash. And if you look at the downwash and upwash, if you look at the upwash outboard of the wingtip, that's the blue line. And we calculated that from a vortex lattice solution. And you'll notice that it follows the bird patterns exactly. Birds can actually feel when this happens. By the way, Jim Usherwood just published another paper in 2021, and it's on the flight of owls. And this photo at the bottom, you can see the vortex is not at the wingtips. The vortex is indeed just inboard of the wingtips on this bird. I'm not going to go through this. We've done CFD in order to try and figure out what's going on. We believe that the point at which the stall occurs is about 30% of the way out from the center line. It's not at the center line of the aircraft. And in fact, we have evidence of this actually happening in birds. This is a shy albatross. You can see that the feathers are being lifted where the stall is starting to occur. And it's not at the center line. It's actually about 20 to 30% of the way out. And if you look at the local lift coefficient, you can see where the lift coefficient peaks is about 20 to 30% of the way out from the center line. So this all makes sense. All of this is tracking. It turns out that the first person to describe the twist in the wing of a bird was Nachtigall. He was a German student that was studying at UC, University of California in Berkeley. And he published his paper in Journal of Experimental Biology in 1966 on how much twist was in the wing of a bird. These were pigeons. The amazing thing to me, if someone had actually calculated the lift from these birds, we would have known the answer in 1966, and you wouldn't be sitting here listening to me now. But no one did it in all those years. And so I happened to be the first one to stumble into this answer. And it was only because I had all the information, well, almost all the information. There was about 20% of it that I still had to figure out the thread between the connection between all of these. So we've turned this into a technology and built it into these little gliders and instrumented them, fully instrumented. And we actually went out and we found that indeed we have proverse yaw. This is pitch, roll, and yaw. And these are all to the same scale. So the red line is pitch, and you can see that there were some thermal activity that day, like driving down a gravel road. The blue line is the roll rate, and this is about plus or minus 30 degrees a second on this maneuver. The green line is the yaw rate, and you notice when the blue line goes up, the green line goes up. And when the blue line goes down, the green line goes down. That means yaw and roll are connected in the same sign. So as you roll left, the vehicle will yaw left as well as roll left. So we wanted to see how strong this was, and we went back and we identified that with the control surfaces. And that's what the data points over on the right are. The blue line is what I calculated using Prandtl's lifting line. If you reduce it for the scale of the airplane that we were flying, it's about 25%. So we reduced the slope by 25%. We kept the zero at the same point. And that's what this airplane should have generated. And then those data points with the scatter are shown on there. That was the first indication that we did. We did this in 2013, by the way. And that was the first indication that truly this yaw and roll were connected in the way that we thought it was. So in 2015, I did this with students again. And this time we had 58 data points. I had two groups, and we ended up with the red line and the green line. Excuse me, the red line is the old Prandtl data. The green line and the blue line are the two teams that I had between the two students. And I forced them to have their uncertainty on each of the data points they generated. So this was the way we knew we were on the right track. We have another vehicle, a larger vehicle that we put some aerodynamic test equipment on. We had fiber optics in order to actually measure the deflection of the wing, and hopefully we could invert that and solve for what the load was. And unfortunately, the noise in the system was a little too large. I didn't design the experiment correctly. I made the wing too stiff for the sensitivity of the deflection equipment they had. On the other wing, we had a series of pressure ports, and we actually built, oh, I want to show you. Let's see if I can make this do this. Okay, this is what it looks like when it flies. This is the second flight of this vehicle, by the way. And large rubber band launching the vehicle. The vehicle weighs about 25 pounds. It's a 25-foot wingspan. We're off the rubber band now. The deflection of the control surfaces is direct from the little control stick on the radio control unit to the vehicle itself. There's no feedbacks. We're not augmenting the data that's coming into any sort of a flight control computer or anything. This is strictly from the stick to the control surface position. And you can see how well behaved the vehicle flies. And it was a day just like today. My pilot complains that these gliders don't like to come down. And I told him that I designed them to stay up. I don't design them to come down. That was a good day. Okay. And so this is the FOSS data that I just couldn't, you can see the amount of noise that's in the system. I just could not get this to work the way I wanted. This is the pressure instrumentation that we installed in the vehicle. And here's the actual pressure data that we got over the wing. This upper left is near the center line of the wing, and then the lower right is all the way out at the tip. And if you think about the red is the upper surface and the blue is the lower surface. And if you measure the area of each one of those, that is the lift at each point. You can actually see how the lift tapers off as you come from the center line out to the tip. And in fact, this is what it looks like when you get the data back. And you can notice out there near the tip that the red and the blue do not necessarily stay where they're supposed to be. And that's because of the deflection of the control surface. Okay. So this is what we actually got for the span load. The red is the 1933 paper from Prandtl, and the black data points are what we got out of our experiment with the uncertainty bars. And I was over the moon when we got this result. This was just an amazing day when we got all this data. We have a large vehicle that actually flies. It's intended to be a hang glider. It's only flown a few times, but it's the most mind-blowing thing to see someone actually flying in something that you've created in your own mind. I was quite blown away this particular day watching it fly. It flies beautifully at about 30 miles an hour. We towed it with a pickup truck, and every time we would stop the pickup truck, they would release the tow rope and the glider would just glide down. It was really incredible to see this happen. We have wind tunnel data. It was tested in the 12-foot low-speed tunnel at NASA Langley. And if this works for a wing, of course, it would work for a propeller blade as well. You get a slightly different solution because of the forward advance of the propeller blade through the air. but it does work. And again, all my students along the way, all of these students are just amazing. This was the team that I had in the fall of 2015. These are the students that I had in summer 2016. The one on the left is the same girl that was talking to the astronaut way at the beginning. That's Rebecca. And we have students come from all over the place in the United States to do this and to work on this vehicle. And finally, 2018 was the last year that I had students that were working on it. They've had a few students who've worked on it since then, since I've left NASA. And I've actually gone back. I still have a badge. I get to go back and talk to the students and give them a hard time. And this is Red Jensen. He's my pilot. And he is just a screw up all the time. Real quick, there's a total efficiency increase. If you do everything, the increase in the wing efficiency, eliminate the tail, and then increase the propulsive efficiency. For aircraft, the total efficiency increase is almost 70%. In 2011, world jet fuel consumption was about $134 billion. I think today it's about $180 billion. Last year, of course, was a disaster for everyone, but the current consumption rate is right around $180 billion. At that time, 134 billion, we could have saved about 55 billion in jet fuel. If you had applied this to turbines and power production, the world GDP in 2011 was about $70 trillion. World power production that year was $12 trillion. And we could have saved about 1.85 trillion in power production because of the improved efficiency of turbines using this idea. So this is what I've proposed, and once again, I'm still talking to bird people, and they're the ones that seem the most accepting of it. And oh, by the way, in 2015, my students showed up with a can of paint, and the chief scientist, his parking spot was number 21. And so the students went out and they painted my parking spot, defaced it with a can of paint. And it was that way until the day I left. I love it. Okay, I'm going to turn this back over to you, Vered.
Yes, thank you very much. It was very, very interesting, and I was really thrilled to hear it. You have applause from the audience.